For this lesson, which is the third of our review lessons leading into the course, we're going to be focusing on the idea of factoring quadratic relations. And we're actually going to be focusing on the idea of factoring in general. But the purpose of doing that is to revisit the idea of factoring in terms of quadratic relations. In the previous review lesson, I looked at expanding and simplifying quadratic relations. So if you haven't looked at that, or if you didn't feel like what we covered in class really covered that for you, you might want to go back and take a look at that before you look at this one. When we deal with quadratic relations, there are three forms for the equations. There's standard form, factored form, and vertex form. And the way that we move between those is through these various processes. Expanding and simplifying is the one that is used most commonly. If we're going to go from factored form to standard form, we expand and simplify. That means we multiply everything out and collect like terms. Or from vertex form, same idea. The process to go from standard form to factored form, obviously given the name factored form, you might anticipate this, is the process of factoring. And then there is the process of completing the square, and that's how we go from standard form to vertex form. There's also a way to actually go from factored form to vertex form, but it's not a process. It's more of a it's more of a solving. It's more like solving a problem, because you are able to deduce certain pieces of information from factored form that take you to vertex form, but there's really no good direct path between them. If you're really good with this stuff, then you can work your way between these, but we don't teach this as a particular process. So generally, if you want to go from factored form to vertex form and you want to follow one of the processes that we've covered, you would expand and then you would complete the square. This one we make use of the idea of symmetry. We substitute in points and values that we know. So it can be done, and if you feel comfortable with the material, you might want to think that through a little bit more, but that's not what I'm going to be focusing on for now. What I am going to start by looking at is going to be the idea of common factors, and this is something you're going to hear me say a lot in this course and in future courses. The first thing you always want to consider is common factors, and in order to do that successfully, you need to have a pretty good notion of what constitutes a factor and what you can do and what you can't do. So let's take a look at this expression: 8x cubed minus 6x squared y squared plus 4x squared y. So as you can see, this is not a quadratic expression that we're trying to factor. This is just a general expression that we're trying to factor. It's made up of three terms because we have three separate pieces. So these pieces are connected to each other through multiplication and division. In this case, it's all multiplication. And then the thing that separates them is either addition or subtraction. So that's why we have one set of multiplication or division, second set of multiplication or division, third set of multiplication or division. That's why we say this as three terms. So the first thing you want to do, and hopefully you get to the point where you do this in your head, but you want to take a look at the constants, the things that are not variables. So the numbers, 8, 6, and 4. I'm not going to worry too much about positives and negatives here. We're really focusing on the coefficients themselves. And so between 8, 6, and 4, what is the greatest common factor? What is the largest number that divides evenly into each of these? And the answer to that is the number 2. 8 divided by 2 is 4. 6 divided by 2 is 3. And 4 divided by 2 is 2. So that's what we mean when we say divides evenly. It means that when I actually perform the division, I get a whole number. So 6 divided by 2 equals 3. 4 divided by 2 equals 2. I didn't get any fractions or decimals. Now, it's harder to apply that here. It's harder to see, but you might actually want to go through this process where you actually write things out if you're not sure. So let's take a look at the variable terms: x cubed, x squared, y squared, x squared, y. So what is the greatest common factor that fits in there? Now the way you might want to think about this is, well, x cubed is x times x times x. So what's the largest variable term that I can divide this by and not get a fraction? So in other words, have things divide out evenly. Well, I can divide this one x, x, x. I could divide x cubed by x cubed. And of course, you can divide anything by itself, so that's not particularly helpful just to start there. I need to think of all of them, and I need to think of the biggest thing that will fit into all of them. So I've got x times x times x divided by something. X squared y squared, that's x, x, y, y divided by something. And then x squared y, that's x times y. So I can divide all of these by x because those x's divide out. If I divide this by x, if I divide this by x, those x's divide out, those x's divide out. I can divide, looks like there's another x I can divide everything by. So I can divide by x, I can divide by x, I can divide by x. And now lastly, well, I could divide this one by x, but there are no more x's for me to divide by here. So that's not an option. I could divide this one by y, but there are no y's for me to divide by here. There are no, well, there's a y for me to divide by here, but I need to divide by the same thing everywhere. So it looks like my answer is the x times the x, which is x squared. So that is my greatest common factor of the variable terms. So the way that I'm going to do this is I'm actually going to take out the greatest common factor of 2x squared. And now that I've done that, well, what that really means, when we say divide out or factor out 2x squared, what that really means is I'm going to take my original expression, 8x cubed minus 6x squared y squared plus 4x squared y. Let's make myself a little bit of room here. Okay. And dividing out 2x squared means that it's essentially the same thing as just dividing each of these individual terms by 2x squared. Because if you imagine reversing this, if I took 2x squared and I multiplied it back into this bracket, all of those 2x squareds in the denominators would divide out. But by doing that, I'm going to leave my 2x squared in front. And now I'm actually going to say, well, what is 8 divided by 2? 8 divided by 2 is 4. And what is x cubed divided by x squared? That's just going to leave me an x. I've got a minus sign and a plus sign here, so that's going to be negative. 6 divided by 2 is 3. X squared divided by x squared is just 1, so I'm not going to write anything to represent that 1. And then y squared is on its own, so that's going to be negative 3y squared. I've got a positive divided by a positive, that's positive. 4 divided by 2 is 2. X squared divided by x squared is equal to 1. So that I'm not going to write the 1 to represent that. And then y is by itself. And so now I've actually taken out the greatest common factor and I have factored this expression. Now another way that we might take out common factors, and it's a lot more difficult to see, but it's a super useful strategy, and it's actually something we make use of when we start to factor quadratics, is something known as factoring by grouping. So if we take a look at the polynomial that you're given here, AC, BC, AD, BD, there is no single variable that is common to everything. We've got A appears in the first and the third, B appears in the second and the fourth, C appears in the first and the second, and D appears in the third and the fourth terms. So there is no single variable that I can take out. But what I can do is what's known as factoring by grouping, which in this case, whenever you factor by grouping, you want to group together equal numbers of terms. So because this is 4 terms total, the only group that I can make would be a group of 2 and a group of 2. So let's take a look at a group of 2. Is there anything that that first group of 2 has in common? Well, it turns out that first group of 2 has the variable c in common. When I factor out the c, so I start with AC, but I divide out the c, or I factor out the c. Well, that leaves an a. And I have BC, positive BC, so I factor out the c and that leaves a b. Plus, whenever you do this process, you always want to keep whatever this sign in the middle is. And now I take a look between AD and BD. There is a common factor of D, and I divide that out and I end up with A plus B. Now the reason why this is significant is because I now have A plus B here and A plus B here. So if I said something like let x equal A plus B, then really this is the same thing as if I had cx plus dx. But the common factor between cx and dx is the letter x, c plus d. But x is not what we started with. We started with a plus b. So I can actually, now I can take out the a plus b as a common factor, just like I took out the x over here. And then what's left behind? When I take this first piece and I divide out the a plus b, that leaves me with a c. And this second piece, when I divide out the a plus b, that leaves me with a plus d. And you can see now that this is in a factored form. This is now a binomial times a binomial. If you need to convince yourself that this worked, you could always use FOIL or the area model and expand this back, and you would end up back where you started again. Okay, now what about trinomials? So now we're getting into quadratics in general. This applies to all trinomials, but specifically we're going to be looking at trinomials that are in a standard quadratic form. A couple of ways that we can do that. One of them is we can use algebra tiles, or the extension of algebra tiles to do on paper is known as the area model. So what we do there is we model this expression as an area, and then we have to make a rectangle or a square of some sort, and then we derive, or we get our factors from that model. Algebraically, we have to take a look, we kind of have to break things down. We have to perform an analysis on this expression where we want to take a look at the coefficients. Super important. We're going to be looking at the coefficients of each term, and then we're going to perform this process called decomposition. And I'm going to go through this to give you a refresher on what that would entail. So we normally, when we do this, we normally start with the algebra tiles because it's actually the easiest thing to visualize. So if I have x squared minus 5x plus 6, the way I'm going to start is I always recommend you start with the first and last. And even when we get into the algebra, we'll be focusing on first and last to start. So x squared, there's a single x squared tile. Plus 6, I'm going to need 6 tiles here. Now there's a couple of ways that I could orient these things. So for example, I could do all 6 of them in a row like this. Or I could do a 2 by 3 rectangle. And I could also have done 6 in a row vertically, but that actually doesn't matter. So what you want to do is you have to come up with a way of orienting these things so that you can fill out the rest of this rectangle. And so as it turns out, I've laid it out in the way that I need it now, because I take a look at the middle term now, negative 5x, and I realize that I can put 1, 2, 3, so there's negative 3x, and then if I put another 2 of them over here. If I had gone with my original, which was I started with something that looked like this is actually going to fail. And it's going to fail for a pretty subtle reason, and so I think it's worth illustrating. So you might say, okay, well, hold on, I can do the exact same thing by bringing down 6 negatives because I need 5 negatives, but oh, I could put 1 positive in there. You might think, haha, I've shown you that that way also works. But it turns out this way does not work. So let's first of all, let's go over here. This one is x by x. This is -3. This is -2. And the important part that I want to focus on is here. -3 times -2 is equal to +6. Whereas if I go over here, there's an x, there's an x, that's a +1, this one's red, this is a -6, and now we run into a problem, which is -6 times +1 is equal to -6, and that is wrong. Whereas over here, this was correct. So it turns out that this is incorrect, and it is only this one that works. So you have to be very careful about that. And that being careful applies with whether you're doing this using Alge-tiles or you're using an area model, which we're going to take a look at next, or whether you're doing this algebraically. So algebraically, what do we have to do? Now, normally, there's a few ways to set this up. There's a couple of systems or a couple of acronyms we use to help us remember this. One of them is called SPI, and that's how I normally refer to it. And that's where we're looking for sum, product, and integers. Another way you might see this is known as MAN, and that one stands for multiply, add, numbers. Okay, but the results are the same. It's just that the way they get written is a little bit different. So the sum would be, what do things have to add up to? And in that case, in the middle, we've got a sum of -5. The product is going to be this, which is the number 1. So it's going to be the coefficient of the first multiplied by the constant at the end. So 1 times 6 is equal to 6. And then we have to find what are two integers that multiply together to give +6 and add to give -5. And there are a number of integers that we need to consider. So for a product of 6, what are the numbers that multiply to give us 6? We could multiply 1 times 6, 2 times 3, 3 times 2, or 6 times 1. And as you can see, these bottom ones are a reproduction of the top one. So you only have to go to those first two. So we don't need those. And now we also have to think about positives and negatives. Is there any way to take 1 and 6 and have them add to -5, or 2 and 3 for that matter? And the answer is no. So these are going to have to be negative numbers, because when I multiply two negative numbers together, I can also get a positive. Well, what happens when I add these together? So when I add them, -1 added with -6 gives me -7. -2 with -3 gives me -5. Well, that's the one that I want. So here are my numbers, -2 and -3. Multiply, add, numbers. Just asks you to do things in a different order. What is the multiplication of the coefficient of the first times the constant? That's 1 times 6 is going to give me +6. What do they have to add up to? -5. And then we go through the exact same process and we find out that our numbers are just the same, -2 and -3. Now that we've done that, we go through the process of decomposition. Now there's actually a shortcut here, and I'm going to highlight that for you after we've done this the correct way. So let's go to the original question. X squared minus 5x plus 6 is equal to, now the decomposition is, I'm going to take this -5x and I'm going to decompose it using these two numbers. So I'm going to write that as x squared But instead of negative 5x, I'm going to write that as minus 2x minus 3x plus 6. The order that you write these, it doesn't matter. You could write that as minus 3x minus 2x. So long as they add up to negative 5, so long as they satisfy these properties, then it's going to be fine. Now we're going to make use of factoring by grouping, which is something we looked at in a previous slide. And if we've done this right, again, the order that you've written these doesn't matter, but you do have to keep everything in the middle like that. So what's common between x squared and negative 2x? The common factor is x, and then when I factor out the x, I get x minus 2. I always keep whatever this sign is, I have to keep that sign. So I'm going to keep that negative sign. And then what's common between 3x and 6? It's the number 3, but I keep in mind that I am now factoring out negative 3. So what is negative 3x divided by negative 3? That leaves just an x. And what is positive 6 divided by negative 3? That's going to be negative 2. And if you need to check your work, you could always re-expand this. Another thing you need to be looking for is that these two factors, the things in the brackets, they should now be the same. If this is factorable, if this can be done, and if you've done things correctly here, this should be the same. X minus 2 is a common factor, and x minus 3. And now this is in factored form. Now, I mentioned a shortcut, and students always love shortcuts. For a simple trinomial, and that means when the leading coefficient is a 1, so when you have a simple trinomial with a leading coefficient of 1, then your answer is actually just going to be, and you can see it here, x minus 2. Well, that's just x and my first integer. X minus 3, well, that's x and my second integer. So you could go straight to that answer. That only applies when you've got a simple trinomial, and that includes a positive 1 on the x squared. Okay, what about the area model? With the area model, it's kind of like what we did with the algebra tiles. We start with the corners, x squared and positive 6. Now in this case, this is pretty simple in the sense that x squared can only be x times x. That's the only way for us to make an x squared. But positive 6, there's actually a number of ways that I could do, that I could make positive 6. And this is the first place you want to start here is take a look at this value in between. That's got to add to a negative. Well, if there's going to be a negative number somewhere here, the only way for me to get positives is if both of them are negative. So that means this tells me this is going to be x minus something, this is going to be x minus something. But what is that thing going to be? So you have some options here, but really I would recommend you go through the exact same process that we went through here, which is we identify the sum, product, and integers. Well, there's our product, positive 6. We know our sum is negative 5. And so our numbers are going to be, this has to be negative 2, this has to be negative 3. Now, getting there, if you don't want to go straight to that, you could do some trial and error. You could ask yourself, okay, what numbers multiply to positive 6? So you might put x minus 1 and x minus 6. And then when you try to multiply these out, negative 1 times x is negative x, x times negative 6 is negative 6x, and then when I take a look at that, I realize that, hold on, negative x minus 6x, that's negative 7x. Oh, that doesn't work. So this is a fail. I have to try again. I could do negative 2 and negative 3. That makes positive 6. Negative 2 times x is minus 2x. Negative 3 times x is minus 3x. Negative 2x plus negative 3x is equal to negative 5x. Ah, that one works. And so from this I get my answer, which is x minus 2, x minus 3, which of course is the answer we came up with before. My preference is that you master this algebraic method. It's going to serve you well. It's a much more of a process, and I think that once you get this down, you're much less likely to make mistakes with it. But it does take practice in order to master it. Okay, a much more complicated problem is with what's known as a complex trinomial, where the leading coefficient is not positive 1. Now that might mean it's negative 1, or that might mean that it's a number other than 1. So to do this, you're going to see how awkward it is with Alge-tiles, first of all. Now, I can't do this because that doesn't make a rectangle or a square. So I have to either do a horizontal line of them or a vertical line. Whether you do a horizontal or vertical line doesn't matter. Plus 2, that means I need two positives here. Now I could orient these either this way or this way. I only have two options. Now that makes this example easier. Sometimes it can be more complicated than this. So let's go ahead and start with this. And it's going to have to add to 7x. So that means in this case, if I did it this way, I would go plus 2 there and plus 3 here. And of course, you don't have to do this. You can visualize it, and you can already see that won't work. That gives me plus 5x. So that can't be right. So I change this orientation here. I'm going to get rid of that, and instead I'm going to bring down 3 more of those. And this kind of thought process is the same thing that you're doing with the algebra model, just on paper. I mean, you can do the exact same idea. Now, because this one's a little bit more complicated, this brings us into what some of the options are. Notice that here I have a 3 by 1 rectangle, and here I have multiples of 3. I could either have had 3 x's, or now I've got 6 x's. Over here I have multiples of 1 because this side length is 1. So I could have 1x or 2x or 3x. So that process can also help you when you're using the area model to come up with your answer. So let's take a look at this algebraically. So now we're going to use, and I've mentioned my preferred method, or it's not preferred, it's just this is my habit. I refer to SPI, sum product integers. So that's the first thing we're going to identify. What is the sum? The sum is equal to 7, and if you want to, you could put signs on there as well, positive 7. What is the product? 3 times 2 is equal to positive 6. So I can see right now I've got positive 7 and positive 6. I'm going to need two positive numbers. So what numbers multiply together to give me 6? I've got 1 and 6. I've got 2 and 3. I've got 3 and then 2, and I can see, oh, I've crossed over. I'm just repeating myself now. I'm not going to look at those. And now I ask myself, adding these numbers together, how do I get 7? The answer is I add positive 1 to positive 6. Now I decompose, so I get 3x squared plus, but instead of 7x, I'm going to write this as plus x plus 6x plus 2. And then I'm going to do what's known as factoring by grouping. So I form two groups. What's common in the first group? X, leaving me with a 3x plus 1 when I factor that out. What's common in the second? I must use this plus sign, and then the number 2 is what's common. And then when I factor out 2, I'm left with 3x plus 1. Make sure you do this honestly. Don't just copy this over to here. You have to go through the factoring process. This is your verification step, is that those two things are equal to each other. And since they are equal, those factors in the brackets, 3x plus 1, and now what's left when I divide that out is x plus 2. And so that is the factored form for this one. Using an area model, 3x squared, positive 2. And so now we go through that same process, which is, okay, so 3x squared. The only ways I can get that is either I could put 3x and x, or I could do x and 3x. So there's really only one way to do this. That simplifies things. If this had more combinations that would give this result, that would make this much more complicated. You'd have to go through more variations. The area model is really good for expanding and simplifying, not as good in my mind for factoring. Again, I would really recommend that this is the technique that you learn for factoring. So in this case, I've got 3x and x. So this side is 3x long. That means that what goes in this box is going to have to be multiples of 3x. So this could either be 3x, this could be 6x, this could be 9x. Now I put 9x there, but it actually can't be that. That's not even possible in this case. I was just showing you an example. So this could be x, this could be, here, let me do this vertically. This could be x, this could be 2x, this could be 3x. But of course, again, it can't be 3x because we need things that are going to multiply to give 2. And so now we take a look. Well, which of these different combinations will work out to give us 7x? And it turns out the answer to that is x and 6x. So that means that one goes away, this one goes away, and so this becomes x, which means this is a +1. And over here we've got 6x, but remember that's coming from multiplying by 3x, so that's going to be a +2. And of course, +1 times +2 gives me +2 overall, and we end up with our answer here, which is 3x + 1 multiplied by x + 2. Okay, finally, to wrap things up, just to remind you, you can always do the factoring the way that I've just shown you, but sometimes the problem presents itself using one of these special patterns, which is either the perfect squares pattern or the difference of squares pattern. If you don't remember these, or if you have a hard time memorizing these, you can always rely on the factoring techniques that I've already gone through. But this can be really helpful, particularly when the coefficients are quite awkward, if things are quite large. And also remember something I said right at the beginning, which is always, always, always look for common factors first. So let's take a look at this first one. First of all, common factors. There are no common factors with variables. There are no common factors with coefficients. Does this satisfy any of my patterns? Well, first of all, I only have 2 terms here, so that means it can't be a perfect square. I look at difference of squares. Is this first term something squared? 25d squared is the same as 5d all squared. Is this second term something squared? Yeah, 144 is actually 12 squared. So this is a difference of squares. This is like a squared minus b squared. So I could write that as a minus b, which is 5d minus 12, times a plus b, which is 5d plus 12. And that saves me all the trouble of having to go through SPI or the area model or anything like that. Taking a look at b. This cannot be a difference of squares. There are 3 terms in it. So what we ask ourselves, first of all, is, does it have a perfect square at the beginning? It does. 16x squared is the same as 4x all squared. Does it have a perfect square at the end? It does. 9y squared is the same as 3y all squared. This is a positive. This is also a positive. You have to watch out for that. The pattern a squared plus 2ab plus b squared, or a squared minus 2ab plus b squared. Notice that these are positives no matter what. And the negative sign, so this determines what the sign will be inside the bracket. So in this case, it's going to be a plus, and it's going to be that thing all squared. Now, you do need to check something, which is this middle term is 2ab. So I have to take what a is, which is 4x, multiply that by b, so 4x times 3y is 12xy, and multiply that by 2, which is 24xy, and that works, which means this one is a perfect square. Now, what about these ones? Well, in these cases, the number 18 is not a perfect square. I've got 3 terms here, but 18 is not a perfect square. But don't neglect the idea of common factors. It turns out that, well, 18 is divisible by 2, and that turns it into 9, which is a perfect square. 60 is divisible by 2, and 50 is divisible by 2. That turns it into 25, which is a perfect square. So I can take out a 2. I've got a p squared, a p, and no p variables. I've got a q, and a q. So I can actually take out the common factor 2q, and that leaves me with 9p squared minus 30p plus 25, which gives me a perfect square pattern. I keep that 2q in front. 9p squared, that's the same as 3p all squared. 25 is the same as 5 all squared, and then I've got a minus sign from this middle term, and then I do that last check, which is 3p times 5 is negative 15p, and then double that is negative 30p, and so I'm quite confident that that is correct. What about this last one? Common factors. There's no perfect squares. Well, there are perfect squares in the variables already, but the leading coefficients don't have perfect squares. But if I divide everything by 2, I actually end up with 49a squared minus 16b squared. 49a squared is the same as 7a all squared. 16b squared is the same as 4b all squared, but this is only 2 terms. That's a difference, so that means it's actually going to have to be the first one subtracted and the second one with addition. And for any of these, you could always expand and simplify out to double check your answer. Okay, that's it for the review of factoring. I went through that pretty quickly, although I think the lesson ended up being still quite long. This is a pretty serious topic. You really do need to take your time because this is something that's going to come up again and again, not just this year, but in next year's courses as well. So we're working out of the textbook now, getting into some homework problems as listed here.